So, good morning, ladies and gentlemen. Welcome to this lecture, one of the most interesting lectures of this course, to remind where we are. Recently, we have learned the technique, the tool set of creation and annihilation apparatus, and now we are busy with applications. First application, a week ago, was magnetism, solid state, condensed matter. What I'm going to do today is to turn to, well, perhaps even fancier phenomena as far as I'm concerned, and I'm doing superconductivity for almost 40 years. It's the most fascinating topic of condensed matter physics, and perhaps I could even explain why. But well, perhaps some of you have been also fascinated by superconductivity, just coming as schoolboys, schoolgirls to this university. Then you saw, well, levitated magnet. Who has seen levitated magnet? All right, so you know what superconductivity is, and I will provide you some technical details. All right, first, the overall outline of this lecture. We will talk a little bit about superconductivity for general definitions, what it is. Next, we are going to formulate a model which describes superconductivity. We will understand that it is attractive interaction, which is important. We will talk a bit why electrons can attract each other. Right. Then we go practical. Similar to what we did in magnetism, we will look at trial wave function. But that will be a fancy one. It would have some structure, mixing the states with different number of particles. Anyway, we can write this wave function. We can proceed with this in a very similar way we proceeded with magnetism. We compute energy corresponding to this wave function, and we will find the minimum of this energy varying the parameters of this wave function. And we find best fit, best approximation to the energy of, to the ground state of a superconductor. Good, that will take quite some time to get to the answer. After that, we will talk about the results, about excitations at the background of the state. We establish new ground state, new vacuum. There must be excitations. We will look at excitations, particles and quasi-particles in superconductor. Fine. And then second part, or perhaps a part of the second part, it is a shorter piece. I will talk about superfluidity, a phenomenon which has some similarity to superconductivity, but yet different. Roughly, superconductivity is about fermions, and superfluidity is about bosons. For a change, just to expand our overview, we will treat superfluidity with different method. We will treat it as an example of field theory. We will talk about Bose condensates, and we will find actually quite some similarities between particles and quasi-particles for superconductors and superfluids. That's the plan on the lesson. Third, we follow some general scheme. We have a problem, we have trial function, find ground state, look at excitations. Right? Good. Let's go with this. Fine. Superconductivity has been discovered relatively recently. Unfortunately, not in Delft, but very close to Delft, you know. Shall I tell a kind of a legend about discovery of the superconductivity? This is to stress that it was very unexpected by physics of that time. It could have been that superconductivity is not discovered by this year, just if people were not essentially explorative. So Professor Caroline Honest was very explorative at the time. He's discovered a method to go to low temperatures by liquefying gases, by liquefying helium. So it worked like that. He had a system of pumps, and it kind of pumped it boom, 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 for a couple of weeks. Then he got several liters, several gallons of liquid helium. And before it evaporated, he had to do a bunch of experiments. And that days, he had an extreme shortage of hands. He did experiments, his assistants did experiments, but still hands were required. I don't know about your management abilities, how would you solve this problem? He solved it in a very creative way. By that time, on streets of Leiden, there were still young people having nothing to do. And for little pennies, they did experiments for him. Right? And one of the boys, when supervised, when people looked at it, did something very wrong. He has broken an expensive piece of apparatus, ohmmeter. So the results of measurement represented the resistance of mercury just dropped to zero. Well, that boy has been sent away without paying. That's why we will never learn what was the real discoverer of superconductivity. But what professor was kind enough to repeat this experiment and find that indeed in mercury and in many, many metals at sufficiently low temperatures, there is no resistance at all. Right? That is one of the manifestations, experimental signatures of superconductivity. Another one, it is about the experiment you have seen as when coming to this university for open days. Levitation. It is so that magnetic field is expelled from superconductor. It costs too much energy for magnetic field to penetrate it, so it's expelled. And owing to this, if you put it on the magnet, there is levitation. Magnetic field expulsion, Meissner effect, you call it. Two effects, and that's been observed experimentally for many, many years. Only in about 50 years after the discovery, people could come with a good theory about this. What I will present today is a little bit simplified description of this theory, Bardeen, Cooper, and Schrieffer. Right. It's not that the phenomenon was not interesting. It's not that people were lazy by that time. These 50 years was a period of most assertive expansion of physics. First half of 20th century. Nevertheless, it took much time to crack the mechanism of superconductivity. Because from theoretical point of view, it was even less expected than from experimental point of view. Right. Perhaps most important property of superconductivity, which is actually utilized in many devices from, I guess the most important modern utilization is superconducting qubits. This is also a case of broken symmetry. While in magnets we can say, well, it's just rotational symmetry which is broken. The symmetry broken in superconductivity is very good, it's gauge symmetry, and actually responsible for zero resistance for expulsion of magnetic field. It is a fact that there could be supercurrents in superconductor, currents which flow without voltages. Fine, that was very general, I would say, fact, at least about superconductivity, which I presume you all know. Any questions at this part? Fine. Let me go towards theory of superconductivity, formulating a model, assuming a mechanism for what is going on. When we will put it into formulas, it would be better than I put it now. At the moment, I want to give some explanations, well, at this particular level. As a cartoon. So the relation of this cartoon to superconductivity is more or less like the relation of this cartoon to actual Barsky. Fine. So what are elements of the cartoon? Actually, the requirement for superconductivity is attractive interaction between electrons. As we will see today, it doesn't matter how strong this interaction is, very little attraction will work in established superconducting ground state. First of all, it looks like rubbish because we know that electrons are charged and they should repel each other. Even as we discussed earlier, the interaction is screened, it's still repulsive. Right. Nor, they say, there is also a source for attraction between electrons. This source is something which is absent in vacuum. It is a lattice where electrons are situated. In short, electrons deform the lattice, and if two electrons become closer, they deform it less, and that costs less energy, and that would provide attraction. Does it sound correct? Let's go to Scheveningen. Now. Let's take a batute. Remember that? There is a square piece of rubber. You can jump on it. Okay? If you put yourself on batute, you would deform it. You would create some potential relief. Okay? So imagine second person jumps in batute. There will be also deformation. Now, if these deformations become to overlap, you feel attraction to this person. This is what is going on for electrons, but instead of two-dimensional batute, we have three-dimensional lattice, and electrons deform atomic positions around themselves. So this is a source of attraction. Right. Then, okay, there is attraction. Why does it help? Why does it help in establishing superconductivity? Again, it's at cartoon level. It's a way to explain lengthy formulas. Right, if electrons are attracted, they form unions, they form pairs, they form Cooper pairs. Cooper is a pass. Electrons couple each other, they come with opposite spins. Let me just draw it. And this opposite, usually they come with opposite momenta. This union of two fermions is a fermion boson. Right. So fermions minus, 2 times minus, plus, it's a boson. Yeah?
So Jaroslav told us that there's still discussion going on whether Cooper will be photons or other thing, because you mentioned something with the wave function being antisymmetric.
Yes, you're perfectly right. But we are on this level, okay? So if you have heard about about other kids in kindergarten, please listen to me. Yes, indeed. Okay, I'm describing a cartoon. And the cartoon says, well, if there are bosons, they can go to the same level. They all go to the state with zero momentum. There's plenty of those. So Bose condensate is formed. Right. These Bose condensate provides all superconducting properties. So when a current is flowing, it is not a flow of particles which can scatter or dissipate. It is a flow of condensate. That explains everything about superconductivity, again at cartoon level. But already, as you said, there are questions arise. For instance, are these Cooper pairs really particles? really separate objects. Eventually, more or less from our calculation, we will see that they're not. Nevertheless, this cartoon works. At least the main features are there. So let us try to be more practical, write more formulas, and understand how these features emerge. What is important from the cartoon, and which I will immediately express in terms of operators, it is an operator of creating a Cooper pair. So just create electron with momentum k, vector k, and spin up, and simultaneously an electron with opposite momentum, opposite spin. Thereby, I will create a Cooper pair. It's an operator. Right. Now I wanna deal. Yes. You cannot see the screen, you mean? Is it better now? Yes. Fine. Right. So I will start with general formulation of interaction that we remember first time we encountered it in lecture number 3. Right. So we have 4 creation and annihilation operators. There's plenty of terms here. And since there are too many terms, I would like to make a restriction approximation. And in this operator, I will only keep terms where electrons come with opposite spins and 0 total momentum. Good. Why is it so good? What is the relation with Cooper pairs? If I do so, if I concentrate on these terms, I'm able to express the interaction in terms of creation and annihilation operators of Cooper pairs. Fine, at least some use of this Cooper pair concept. Moreover, it becomes a double sum, right? As we did it when we did an interaction for Cartry, for Fogg, remember? From double sum, we have a square of the sums. So here we manage to express it as in terms of Cooper pair operators. Good. And what we see, what is important in this construction is not every operator of creation annihilation of Cooper pairs. Rather, it's the sum which is important. Fine. That gives us an opportunity to rewrite it in a simpler fashion. Just introducing this operator, delta, which is a superposition of creation operators of Cooper pairs. Fine. So the interaction part of the Hamiltonian just modulus squared of this operator, so to say. Good. This is simplification of the interaction, but one can prove that for superconductivity, these mere terms are relevant. Good. Now let us make the constructive assumption. Let us invent trial wave function. Again, we would not be able to solve the problem exactly, even with approximation which we did. What we can do is to take a wave function which you can treat, which you can understand, and we'll try to minimize its energy. All right. Let us see. To get an idea of this trial wave function, I first take something which we know. The ground state of non-interacting Fermi gas. What do we do when creating the state? We feel all states within Fermi sphere, and we feel no states beyond Fermi sphere. Right? Now I notice that I can't rewrite it in terms of creation and annihilation operators, in terms of Cooper pairs, because in this field states all electrons come in pairs anyhow. Fine. So this is a non-interacting Fermi gas, and now I notice, look, for some states I did create a Cooper pair. For some states, I did not. What could be a generalization of this? And generalization is very quantum mechanical. It is a superposition of these two possibilities. So general trial wave function is as follows. For each pair of the states with k spin up minus k spin down, we create a superposition. A superposition of non-Cooper pairs and single Cooper pair. The coefficients of this superposition, kind of probabilities to create or not to create, are these U's and V's. And those are parameters of this wave function. So if you wish, it's a generalization or the ground state of non-interacting Fermi gas. They just made it fully quantum mechanical, allowing for superpositions of two possibilities. Fine. That was eventually a hunch of this Bardeen-Cooper-Schrieffer gas. Yes, please.
So you don't consider a single particle state?
No. No. So it's either 0 or 2. We will see how single occupied states can come into this game. Very good. Now we can just apply mass scales to deal with this function. What is the goal? What's the problem? It is to compute the energy corresponding to this trial wave function and minimize it with respect to U's and V's. All right. For that, yeah, if the problem is complex, you better do it piece by piece. So I want to introduce some structures, some small pieces, number structure, number boxes, where I can deal with this problem in a very simple fashion. Right. And for this, I pick up for each pair of k minus k as opposite spin, I pick up 4 possible states. 0, no particles in this state. 2, both states are filled. I guess the bracket must be here, sorry. Or I could indeed make single occupied states. The spin up plus, spin minus. 4 possibilities. Having 2 states, you cannot fill it in differently. All right. So I have a basis of first states, which I can immediately simplify to 2 for our wave functions. Because, as you said, we don't consider single electron states. We just concentrate on the subspace of 0 and 2. Fine. And I want to understand how the apparatus would look like in this subspace. Right? That's a subspace. So, for instance, if I create a Cooper pair, what will happen? The only matrix element is between 0 and 2, out of diagonal. Conjugated operator, annihilation. Here it is. Now I also need the sum of occupation numbers. Okay, and this basis is diagonal matrix, right? So either 0 or 2. So here it is. The matrices in this basis. And now I'm ready to deal with my wave function, trial wave function. Computing energy separately in each block. In order to make it good, I've got to normalize this wave function. But well, as far as I'm concerned, it is simple. Right, why is it simple? This wave function is a direct product of wave functions in different number blocks. So I only have to normalize it in each block. This is what I want to normalize. And in this basis, 0 to basis, this is just wave function like this. So how would you normalize it? Well, the sum of squares of both coefficients must be 1. That's it. We establish this relation, normalization relation. We will use it when we will compute the optimum of energy. Right? That's condition which normalization provides us. Next step. It's like a magnetism, but just wave function is different. Let us compute kinetic energy. Right, so how we can do this? It is handy to count energy from Fermi energy, from chemical potential. All right. So these electrons epsilons are electron energies counted from Fermi level. What does it mean? If you forget about superconductivity, then if epsilon is positive, the L level is if energy is above Fermi level, the level is if energy is above Fermi energy, the level is empty. Okay, good. More complex question. If epsilon is negative, the level is fine. So that's handy to introduce these epsilons. Very good. So I'm ready to compute kinetic energy. And look, for each number box, kinetic energy is just the sum of occupation numbers for two levels. Okay, we know how this matrix is expressed in 0 to basis. We know the wave function. Okay, we can compute the energy. Here's the relation. Here's the answer. By writing it like this, I've already taken into account that sum of that u squared plus v squared is good. That's kinetic energy, and it makes sense for non-interacting Fermi gas. If we just look at this expression which we derived, then how to achieve minimum energy? If epsilon is positive, you wanna push V to 0. If epsilon is negative, you wanna maximize V. You cannot do it till infinity. V's are restricted by 1. Right, good. And that's the optimum of kinetic energy. So if we have superconductivity, if U's and V's are not like in non-interactive gas, there is energy cost to pay for that. Good. What does it mean? It's also the same situation as with magnetism. We want to utilize interaction as a source of the effect, as a source of superconductivity. The same as it was with magnetic state. Right. So, potential energy. I still want to make a little trick before I actually compute it. This little trick is as follows. The expectation value of interaction energy, as we derived, it's a sum of, it's a product of two squares. So it looks like average of two fluctuating variables squared. Okay? Expectation value, it's in fact an average. All right? And that D is this delta, sorry, not the delta, is contributed by plenty of Cooper pairs. And if a value is contributed by many independent values, then by virtue of central limit theorem, that's what it is called, statistics, very strange, rather undemocratic this here. You can replace this value with its average. Fluctuations of this value are small. To this end, we replace average of squared with a square of two averages. Fine? Great. Let's work with this. Good. So that is that allows us to compute this average delta. Average delta, just by definition, is the average of let's iterate that. How do we compute this average? Precisely in the same way, we go to number box, where Z is 2 by 2 matrix. We implement our wave function. So that's what we get. Shall I make some drawing to kind of initiate your imagination about matrices? Okay, some people don't like them, I make drawings. Let's see, sir, what is that? There's wave function. In one of the number boxes. There is, let's see, that this is a bit complex. And there's an operator coming between them. Operator that we have derived, it creates a Cooper pair. So it has all zeros except this position. All right, now we do vector matrix vector multiplication. We're done. Here we are. So, well, and then in order to compute the whole energy, we just need to square this value. Good. We are ready to minimize. Let me just do it quickly since I don't have much time. There's plenty of fine mathematical details. Nothing is overwhelmed, but it's quite an exercise for mathematical mascals. Right. First, let me explain what we are doing. We express energy in terms of U's and V's. Then, in order to find the minimum, what do we have to do? We should find the variation of this energy with respect to all parameters and put this variation to 0. Okay? How do we find a minimum of something? We just put derivative to 0. Right. So we vary it, and okay, it has variations of V's and U's. Right? Variations. So I change V a bit, delta V. I computed the difference. I changed U a bit, delta U. I computed the difference. Okay, but now I have to recall that variations of U's and V's are not unrelated, because they have to satisfy normalization condition. So here we are. Good. Then instead of varying separately in delta V and delta U, you can just vary in delta U. Here we are. We expressed products of U's and V's in terms of delta. We also can compute with the same method the energy which is accumulated in a given number box. All right, I guess I would like to make a break, like 6 minutes break at this part. Thank you for your attention. Fine. So we did this minimization. What's the difference with magnet? In the magnet, we just had single parameter polarization. Now we have parameters in each number box, okay, dependent parameters to minimize use in this. But, well, we have found this. We have expressed it in terms of delta. We don't know what delta is. How to proceed further? Yes?
What's like a question about the derivation? Why do we vary only like the normal part, the moments, not the continuing part?
Okay, it doesn't matter because each complex number is just two numbers, right? Then we can vary these two numbers. We can vary separate real part and imaginary part of each U and V. But it also suffices if we only vary U and don't vary U conjugated. Because anyway, it still has two parameters. Delta U is complex, delta V is complex. Does it answer the question?
So if we try to do the derivation with the conjugate versions, we would have the same answer.
Fine. Then let us understand how we can know delta. It's a very important concept. Comes in many similar calculations. It's called mean field approach. It's also used in classical thermodynamics. Right, it's self-consistent. We know use in this, and we know in terms of delta. And we also know delta in terms of use in this from the very beginning, already before minimization. So now we can combine these two formulas together and find what they called self-consistency equation. Good. So that's what we knew before minimization. Now we substitute this into this. Here we are. Okay. We have a sum over k. We know that as usual in this course, we have to replace it by integral. And then we have cancellation of volume. Fine. I would like to integrate over energy instead of integrating over wave vectors. To this extent, and it is, I believe it is similar to one of the homework problems. Oh, no, not yet. Sorry. To this extent, we just introduce density of states. How many states of quantized K are there in a small interval of energy? That nu is gonna be density of states. And it's okay because we have only energy here. And I also assume that I'm somehow very close to Fermi surface. And there I can regard density of states as a constant. Here it is. After that, it becomes a simpler integral. You could say, oh, okay, now I can take this integral. Not yet. If you look at it carefully, it will diverge at large epsilon, logarithmical divergence. But here, it is common in physics to disregard logarithmical divergence. Divergence is very weak, and one could deal with that just by introducing a cutoff, right? You just say, well, now I'm working close to Fermi surface. I don't know what happens at higher energies. Why don't I just cut them off at some energy? Good, cut off energy. After that, can compute this integral. It's eventually log. It's a log, and this is self-consistency equation. The solution of this equation is as I write. Good. First of all, it seems large. It is proportional to cutoff. Cutoff is Fermi energy, so it's supposed to be big. Not really, because it is multiplied with exponentially small factor. It is exponentially small if interaction is weak. And that appeared to be the case of most metals. So this factor, exponentially small factor, it's a kind of factor of 10 to the 4. That's why in most metals, superconductivity only persists at helium temperatures, 4K. There are superconductors which have superconducting temperature up to 100K, but it's very exceptional. That's bad news, it's small. Good news that any big attraction will do that. As far as sign of interaction corresponds to attraction, there is superconductivity in a metal. Fine, that explains why in around half of metals you actually observe superconductivity at very low temperatures. Good. I want to talk about quasi-particles and particles. So how can I present it in a compact way? Now we have to recall that we also have single particle states. Now we've been dealing with 0 and 2, and we understood that these two states are eventually in superposition, right? And the ground state after superposition is neither 0, 2, it's a symmetric combination, it's a combination. Now let us add a particle. So from ground state, I could go to single particle states, either with spin up or spin down. Strangely now, the same will happen if I will try to extract the particle. Why is it so? Because the ground state has a probability to have two particles. So I extract and I go to the state with one electron. Okay? That's because we don't have definite number of particles in the ground state. So we have a problem with sorting this out, but what we know is excitation energy. Excitation energy, that means we go from ground state energy to the states which are not affected to superconductivity. So this is excitation energy. It depends on delta, it depends on epsilon. So there's always a minimum value of this excitation energy. In order to add or extract a particle, one would have to pay at least delta. Energy gap in the spectrum of excitations. All right. We don't like this. We would like to adjust creation and annihilation operators in such a way that they look kind of like we want. We can add quasi-particle and extract quasi-particle. And ground state is a new vacuum. So if we are trying to extract quasi-particle from vacuum, what do we get? Zero, precisely. That's the definition of vacuum. Okay, let's do this. Let us try to find an operator, gamma, which does the job. And if you try to look for a form of this operator, one can see that this superposition of adding and extraction of particles will result in extraction of quasi-particles. So we have to make linear transformation of operators. If you recall what Max told you, when was it, 2 weeks ago, on Monday, that's precisely it. We have to make linear transformation of creation relation operators to come to new operators to go from creation of particles to creation of quasi-particles. Now it's okay, we cannot kill anything in vacuum, and we can create single quasi-particle, go to the states plus and minus, or we could create two quasi-particles, go into this excited state. Excitation energy is the same here plotted. Here plot this excitation energy. So it costs at least delta to add a particle into a superconductor, which looks very much like what? Also conductor, but where do we have energy gap? Precisely. It looks like spectrum of semiconductor. And it's indeed so. So why we have conduction in superconductor? It's because we also have condensate. And supercurrents are created in condensate. They cannot be particle currents. Good. Kind of out of time. So I want to keep it short. Which symmetry is broken? This is gauge symmetry. What is a gauge symmetry? We can multiply wave functions with the phase factors in quantum mechanics, and nothing changes. Right. Let us see what will it correspond to if we go from wave functions to operators. Well, to figure that out, we understand that in Fock space, the gauge transformation for each particle just is multiplied with the number of particles in this particular state. Good. Then we understand how relationalization operators transform upon this transformation. They also got phase factor. Fine. And if we have a Hamiltonian with the same number of C data and C, we multiply it with phase factor, it stays symmetric. It cancels. Fine, it's gauge symmetry. Our assumption of superconducting state is not symmetric. If one takes creation operator of Cooper pair, does the same transform, it is multiplied with a factor, which means that the delta which we have introduced is also multiplied with this factor, with the gauge factor. So this symmetry is broken if delta is not zero, if we are in superconducting state. Right, and that means that the superconductor, which could be kind of 1 kilo object, the whole macroscopic superconductor is characterized by this quantum phase. So we can talk about microscopic coherent state, and that's also kind of roughly the basis of quantum applications of superconducting. Good, gauge symmetry is broken, and a bit after of time. So let me go to superfluidity. And stop me if I go on with long jokes. Right, superfluidity. Same kind of owners made helium liquid, but it required a little bit more time to discover superfluidity. That's one of the manifestations. In this experiment, we can see the flows of the liquid which go without dissipation. Like electric current in superconductor doesn't cause any voltage, no dissipation. The same you could do for mass currents of helium atoms in this liquid. Right. The only material which can be made superconducting is helium. Why is it sure? Because, well, helium has lighter atoms, and the lighter atoms are the more quantum mechanical, aren't they? That's why superfluidity is observed in helium. Right, what is the origin? Well, the origin eventually was more or less clear from very beginning. That was Bose condensation. We've been talking already about Bose condensation when we talk about superconductors. Here it is, because these atoms, helium atoms, are just bosons. Right. We also have to add interaction. Without interaction, it doesn't work. Bose condensate is not superfluid. Good. Theory has been elaborated many years ago by Landau and Bogoliubov, and theoretical discovery, which, well, if you look at this Fontaine, the idea that symmetry is broken doesn't immediately come into your mind, right? But as we learned from superconductors, the presence of non-dissipative currents hints already that there's a broken symmetry, broken gauge symmetry corresponding to conservation of particles. That's why theorists came with the idea of broken symmetry pretty quickly. Right. Relatively recent activity is a Bose condensation, not in, say, 1 liter of liquid helium, but in microscopic atoms in laser traps. Okay, they could see, say, condensation of a couple of hundreds, say, calcium atoms, much heavier atoms. I don't quite understand why it's better to have 10 atoms to concentrate instead of 10 zillions in helium. Well, but at least they could do it with heavier atoms. It remains rather popular field, also called atoms. Fine, that was fact list. Let us formulate a model. Let me first recall non-interactive Bose gas. And it's simple, it's like a homework. There are massive particles, bosons, but if you think about ground state of the system of particles, you end up with a very simple idea. All particles just go to the lowest energy level corresponding to K0, right? Since they're bosons, you could put all your particles on that. And that's going to be ground state, so it's extra hint to your homework. Right, so it is a fixed number of particles. Now let me move a little bit into this direction of symmetry breaking, because one could have said it at this stage already. Look, it means that energy does not depend on number of particles. The states are degenerate. In this case, it is plausible to think of superpositions of the states. If the states are degenerate, we cannot distinguish them. It's easier to create and maintain their superpositions. What kind of superposition can we make out of states with given number of particles? Or we can, and it's missed here. We can just take this combination, equal weight combination of all states, superposition of all states, which would have phase as a parameter. That will be a state of a given place. But we cannot sort this out at this level because it's too idealized of a model. Let's add some interaction to it. Perhaps it will become better. And okay, perhaps I'm giving you too much. Perhaps I'm giving you the dangerous tools like if I give you a hammer, you could harm your fingers. Who did it with a hammer? Nobody? You? Okay. I don't know if you dislike something in this presentation, please never use the technique. Good. I'm trying to give you more dangerous technique than trial wave function. Since we've been talking about field theory, let's try to make it as a field theory. Right? And what is a field theory? In this case, it's kind of Heisenberg-like. We don't care much about wave function. We would like to look at field apparatus. What are the averages? How they constructed? What are excitations? So in fact, we would like to formulate everything in the language of Heisenberg equation. Which of course would bring us to immensely difficult problem. But there is a good guide to this problem. Since we have many particles, we could imagine for a while that we are doing this classical field theory. Classical field theory, that will be our guideline. Right. Let us see. First of all, let me add interaction into this Hamiltonian. That's, first of all, it's a kinetic energy. I write it in terms of field apparatus. And if I add interaction, this is what I wanted to add. Good, it's the same formula as we've been looking in lecture number 3, 4, and today lecture number 5. The only point, I don't write it in Fourier representation, I write it in coordinate representation. So that's eventually, that pair would make a density of particles. I have to put apparatus in such a fancy order, that comes with that, to have two annihilation operators on one side. In this case, I can exclude self-interaction in my system. Fine. Simplest model, contact interaction. This is delta function. And I have single integral. Fine, we have energy in terms of operators, field operators. Now we can derive Heisenberg equation just by computing the operator with a like we always do with Heisenberg equation. So we have an equation for field operator. How does it evolve in time? If it were a linear equation without that term, or we could solve it very quickly and efficiently. Unfortunately, it's not linear. And then we have non-linear matrix equation. And it becomes too complex. We could not even put it to a computer because those are matrices of infinite dimension. It took us 5 minutes to write this answer. It was easy, but we cannot readily go forward. We have to think in it. Right. And again, one can reason like this. This field operator comes from many, many particles in the same state. So perhaps, like we did already for superconductivity, perhaps we can replace this operator by its average. That's what we do. So instead of the operator, we just take an average, just a number, and solve the equation for the numbers. Which equation? Just to remind you, this equation. So instead of these guys with hats, substitute numbers. Well, this number, oh, I got the wrong side. This number in principle depends on coordinate. But let me look at homogeneous solution, which depends on t only. Then I get it very quickly. Here it is, has some energy, chemical potential, and that chemical potential is related to interaction energy. That's a difference from non-interacting gas, and it makes sense. Well, this chemical potential just effective energy with which all other particles interact with a given particle. Fine. Right. Now we can kind of relate it to particle density. We just making squared of this field operator. Simple. So particle density is constant, doesn't depend on time. And that's actually a solution of problem for the ground state, which looks very simple, calm. It's like a still ocean. Which could be very boring without small waves. So indeed, this solution is too simple to look at boring. It becomes a little bit lovely if we begin to think about excitations. Right, in superconductivity we have to work very hard just to get to the ground state. Well, here ground state comes almost for free. Okay, let's look at excitations. Right. Who of you ever linearized a nonlinear equation? That's good. That's about what we are going to do now. So the idea is to take this field operator as what we have computed, still ocean constant, which depends on time, and give it a small deviation, which is an operator. So constant in main and small operator about it. Good. Then we linearize nonlinear equations. So we keep the terms of the first order only. First order in delta phi. Anybody did practicum planets with me? I suspected that these guys do not survive. All right. Good. Linearization. So we keep terms of the first order only. Most of the terms come very handy and intuitive. Okay, that's linearization is chemical potential. That's also understood. That also proportional to delta psi. That looks incorrect. In the equation for delta psi, we have a term with delta psi dagger, and vice versa. If you have equation for delta psi dagger, there's a non-convenient term with delta psi. Right. But anyway, we can do Fourier transform. We can introduce operators corresponding to this field operators. And we can write down Heisenberg equations for those. Derivative of B, is it something that you expect? Normally we would have energy over there, but there is also this strange term. Good. So it was also kind of blocking point at some level of development of field theory for bosons, for superfluidity. Good. And that particular person has solved the problem. He's been Ukrainian. Good. Was very strange guy. He was a kid when there was a revolution, and the revolution in whatever Russia, Soviet Union, Ukraine was not only a revolution with boom, 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 and public execution. There was also a revolution in all other spheres. They also wanted to be revolutionary in education. So this guy entered university in the age of 12 and graduated in the age of 60. All right. Graduation was in the field of mathematics, and kind of mathematics which considered to be very relevant and applied there. Solution of nonlinear equations, classical equations, hydrodynamics, physics of explosion was very popular in 20th century. Unfortunately, it also gets popular nowadays. Anyway, it was very practical. So he got a splendid career. He got all possible awards, all possible grants. He's been hero of Soviet labor, whatever. Then he got to the age, and he kind of got bored. He asked, well, do you know, guys, what's our interesting problems to solve? As I told him, well, there are some guys doing quantum field theory, and they have some problems. Okay, where are the problems? Okay, that's how he came to this hunch. And it was very natural hunch when you solve in nonlinear equations. Eventually, he just rewrote one of his older works. Good. The hunch was to arrange the separators differently by making superpositions. It's a bit like we just made for superconductivity. Good. So these equations appear to be wrong. We have our view. We want to have right equations. What are right equations? Right equations is something which we know. Equations for Heisenberg equations for non-interacting creation and annihilation operators. Good. How to get from wrong equations to right equations? It's just to make a linear transformation. Since equations are linear, it would also work. Good. So the idea was to write wrong apparatus in terms of right apparatus with yet unknown superposition coefficients. Okay? Good. Alpha beta, if you try to reproduce commutational relations with these apparatus, if you like these apparatus to obey usual commutational relations, that gives a restriction on alpha and beta. It's again what Max has shown to you one month before. He talked about linear transformations of bosonic and fermionic apparatus. Good, that's called Bogoliubov transform. Good, so again, the idea is to adjust this alpha and beta in such a way that equations for gamma are right. Here we have, so just substitute beta to these equations and adjust alpha and beta in such a way that the equations become right. The equation becomes right. The coefficient in this equation, which is energy, which is quasi-particle energy, also becomes different. Here it is return. What is this? So this is just kinetic energy corresponding to certain quasi-momentum. And that mu, as we recall, it accounts for the effect of interaction. Good. So this is in fact a calculation of excitation energies in our Bose condensate. Fine. What do we do when you get this formula? Do you go to sleep? No, not really. Before going to bed, you have to make a plot. I don't know, perhaps you know some other ways to understand the formulas. I always plot it. So let us do this with our expression. So this is red line, which corresponds to our answer. Before reasoning about this red line, let me first plot the original spectrum. Spectrum without condensate, just free particle. Okay, that's going to be parabolic. That would go to 0. That's okay. Well, suppose we want to take into account the effect of other particles. Okay, they come, they interact, they rise energy of each particle. Right, so it is got shifted by this mu parameter which defines interaction. And if we look at sufficiently big K, our answer makes sense. It looks parabolic. And if we also add this chemical potential, it's almost perfect match. But there's also another limit. Another limit is a limit of small k. And we see that the energy is linear in K. What does it signal? It signals waves without dispersion. Light is an example. For light, frequency is just proportional to k. And another example is sound. If you talk about acoustics, if you talk about propagation of sound in condensed matter systems, fluids, whatever, that's the same dispersion law. So the excitations of the condensate eventually sound like at very small q, but if you increase q, look, they become massive particles. They assume parabolic dispersion. Right, that was fascination of the answer what Bogatyubov delivered to us. And that's basic facts which we had to learn about superfluidity. Right, I still have several minutes to, oh, okay, it's about breaking symmetry again, but it's eventually very similar discussion as we had for superconductivity. So gauge transform is multiplied a wave function with a factor. When you try to make it for field operators, they also require a factor. Right? What does it mean? It means that all averages of the operators break gauge invariance. All averages are not invariant with respect to gauge transform. That's why superfluid is also an example of a microscopically coherent quantum state. This quantum phase which characterizes a piece of superfluid. And like gradients of this phase will result in non-dissipative currents in superfluid currents. What is the difference with superconductivity? Yeah, I guess I forgot to mention this. For superconductors, it's a condensate of charged particles. So there is electric current associated with this. Helium atoms are neutral. That's why there's no electric current, but there are currents of particles, mass currents. All right, I guess I'm done with the super effects. We looked at superconductivity, at superfluidity. We have found broken symmetry in both cases, and broken gauge symmetry, which means conservation of particles is somehow broken. That's because the ground states of these superstates are superpositions of different number of particles. For superconductors, superpositions with different number of Kuiper pairs. For superfluids, superpositions with different number of bosonic particles. Right? And we kind of manage to compute quite many things applying our second quantization technique. And there's also an example of problems which cannot be solved without the second quantization. One wouldn't be able to write a manifold wave function for such problems without applying second quantization. Good, so we are right place. We have chosen and considered the right example. Thank you for your attention. Questions?
How does delta take into the fact that there's no resistance?
Delta by itself is not related. The fact that delta has phase is relevant. Delta has phase, and if you change the phase, you go to different state with the same energy. Right? Now, let us assume, because you can recall consideration of magnets, let us assume a state where phase differs slowly from one point to another point. This state will have low energy. That's okay, it's easy to make. This state will have a gradient of phase. And this gradient of phase will produce the electric current. It's the essence of Meissner effect. If you take a superconductor, put it into a magnetic field, there are superconducting currents at the surface, right? They correspond to the gradients of this phase. So the presence of phase is important for supercurrents. And that's the fact that the phase is there is a manifestation of Brocken signature. Good, more questions? Right, thank you again, see you next time.